For the rest of the day today, as we work for the Riemann hypothesis, we want to think about complex functions. With ordinary calculus functions, you think of functions as y equals f of x. In complex analysis, to remind ourselves we're dealing with complex variables, we use different letters. We write w equals f of z. And there's infinitely many examples I could think of here. Polynomials, trig functions even, cosine, sine of z, e to the z. Let's start with a simple polynomial, z squared. You could call this the squaring function. We also, in complex analysis, because of our geometric interpretation, we're going to call it the squaring mapping, or squaring map for short, because we're going to make some graphs that are reminiscent of maps. That's maybe one reason for the name. When I think about such a function, where w and z are complex numbers, I can certainly plug in those complex numbers. Complex numbers do include real numbers. For example, when I plug in the number 4, that is the same as plugging in the number 4 plus 0i. You can think of 4 as being on the real axis in the complex plane, having imaginary part 0, and you would get 16, which you could think of as 16 plus 0i. If I plug in negative 4 plus 0i, that's the same as plugging in negative 4, doing negative 4 squared to give you positive 16, which again can be thought of as 16 plus 0i. Does the geometric interpretation of complex number multiplication work here? Yes, but you have to be careful in how you think about it. There's a complex plane. The real number 4 could be plotted as a point on the real axis. When you square it, you get 16. You are multiplying this complex number times itself. You can think of real numbers as being complex numbers, so I didn't misspeak there. You are squaring the length of this vector. It's got initial length 4, the output has length 16. And you are adding the angle, because the angle is 0. 0 plus 0 is 0. I mean, you can also think of it in radians, at least, as 2 pi plus 2 pi is 4 pi. They're all valid angles for the answer, for the input and the output. On the other hand, for negative 4, its distance to the origin is positive 4, but its angle is not 0 or 2 pi or 4 pi. It's, well, pi is one possibility, but pi plus pi is 2 pi, bringing you back to a valid angle for 16, a valid argument. But we can also plug in numbers that are not real, like 4 plus 3i. We have to square it. 4 plus 3i squared would be 4 plus 3i times itself. Once again, FOIL it out. Get 16 plus 12i plus another 12i minus 9. Right? 3i times 3i is 9i squared, which is negative 9. And then simplify, you get 7 plus 24i. 4 plus 3i is right about there. Its square, 7 plus 24i, is way up here. Think about the vectors. You can check it. I squared the length, and I added the angle. The angle, the argument for 7 plus 24, is the argument for this one times 2. It should be 36.87 times 2, 73.74, I think. You can check it. So I can plug in complex numbers into that as well. In fact, I could plug in an arbitrary complex number into that. What's an arbitrary complex number here? How about x plus iy? Where x and y are real numbers, What's going to happen when I plug that in, leave some space here. I'm going to write some stuff to the left too. I'm squaring this arbitrary complex number, multiplying it times itself. Once again, I need to FOIL. First times first is x squared. Outside times outside is plus ixy. Inside times inside is also another ixy. The commutative property of multiplication works. Last times last is plus I squared y squared. That's the same as minus y squared. I squared gets replaced by -1. Now group together the parts that do not involve the I, that's the real part. And the parts that do involve the I, that's the imaginary part. And we have written f of this arbitrary complex number, x plus iy, where x and y are real numbers, in this form. And what's stopping us from treating these things as variables? This is two multivariable functions of x and y. If I now give w symbols for its real and imaginary parts, the standard thing is u and v, right? W is u plus iv. Effectively, what I've got here is an equation for u and an equation for v. In fact, I could write u equals, abusing notation here, u of xy equals x squared minus y squared, and v equals v of xy equals 2xy. I've got a system of two multivariable functions of x and y. This one single complex function, w equals f of z equals z squared, can be thought about, if you want, as a system of two ordinary multivariable functions with no i's. Right? We could think of it that way if we want. Maybe we don't always want to, but we could. And it is useful sometimes to think of it this way. What I'm about to do now is I'm about to graph these functions, multivariable functions. I'm going to use in Mathematica plot 3D and maybe contour plot to help us understand them. Also see if they're related in some way. It turns out they are. And also think of this in terms of what you could call a transformation, telling us how to find the point uv in a uv plane using the point xy in an xy plane, and I should give the function a name. I personally like using the Greek letter capital phi here. Why? Just because I feel like it. You know, Greek letters are pretty. You have some variety. Okay, this has nothing to do with quantum mechanics here. It's not a psi, it's a phi. Okay, nothing other than me just liking this capital Greek letter phi. And having these formulas, x squared minus y squared and 2xy. And when you think of it this way, you're thinking of this function taking points xy and mapping them to points uv as what's called a transformation. This is a quote unquote transformation. In fact, it's a transformation of the plane. And when I say the plane, I just mean a plane, but it's really, in my mind, it's the complex plane. Yes, I could label the axes with the words real and imaginary, but I also could label them with the letters x and y. You want to have mental flexibility. Kind of like with vectors, how you want to have mental flexibility to draw them as arrows and allow yourself to move the arrow anywhere you want, whatever seems useful. Also related to coordinates, whatever seems useful. Mental flexibility is important in thinking about and using math. So it's a transformation. That's going to be useful too. All right, let's go ahead and do some exploration now with this on Mathematica. One thing I can do is, like you see here, is I can enter the function f of z equals z squared. It's entered. I could plug a number into it, like 4 plus 3i. It's a capital I, again, that is the imaginary unit. So this is what's going to give me 7 plus 24i. There it is. Mathematica's representation in the output of the imaginary unit is sort of a fancy looking I. You can make that with doing escape, double I escape, makes kind of a fancy looking I. That also represents the imaginary unit. This calculation can confirm what u and v are, but it doesn't regroup them. X squared minus y squared, the parts that do not involve the I, group those together. That is the real part of the function. 2xy, the part next to the I, is the imaginary part, the v. I'm going to make a contour plot of u and v ultimately here. But let's make a plot 3D of them first. I'm going to add an extra code here. Plot 3D of u and v. I do need to enter u and v. They're down here, actually. Let me put this up higher. So here I'm entering u and v. Don't be bothered by the abuse of notation. U and v representing both variable names and function names. It's a standard kind of thing to do. So I could plot u, and I could plot v, and see what we see. Plot 3D. The grid is just going to put these plots next to each other. Though they are kind of small, maybe make them a little bigger with image size. 400 or something might make them bigger. Maybe too big. Okay, sorry. By 300. Okay, there they are. What are they indicating? You see, this is the U graph over here. The x-axis goes to the right. That's the same as the real axis in the complex plane. The imaginary or y-axis goes into the screen. You do see as x increases away from 0, the outputs increase. It's concave up in the x direction, so to speak. Reflected in its formula having a positive coefficient for x squared. And concave down in the y direction, reflecting a negative coefficient for y squared. With the other one, with the v, it's 2xy. It's a little hard to see, but the values of this function get large when you move away from the origin in the first or third quadrant, actually, where x and y are both positive or they're both negative. That's where the outputs are positive, getting close to 50 there, for example. And it goes down as you are in the second or fourth quadrant, where up here, x would be negative and y would be positive, and down here, x would be positive and y would be negative, but you're getting negative products for 2xy. So there's the plot 3D. You can make a contour plot of those things as well. These are the level curves. These are where the function is constant. This one's for u and this one's for v over here. Notice you're going toward lighter regions where the function is higher, just like we saw with the 3D surface graph, as x goes away from 0, and toward darker regions where the function is lower, negative in this case, along the y-axis. Here's the one for v. They're kind of similar looking. It's like they're almost like one is a rotation of the other. Is that an accident? No, it's not, it turns out. It also turns out you can show their contour plots in the same picture, and something interesting happens as well. Let's do that. We're going to need to get rid of the shading if this is going to work. So I also need another option called contour shading, I think. Yep. Arrow false. So that I don't have the colors, the lighter versus the darker. I only see the contours themselves. So I'm about to enter this. We're going to see both sets of level curves in one picture. There they are. Pretty picture. If nothing else, this is artistic. But also, those level curves for the u and the v, wherever they intersect at right angles. Isn't that cool? Those are called orthogonal trajectories, orthogonal being basically synonymous with perpendicular. Anytime those cross each other, They cross at right angles. That's not an accident. It's related to nice complex functions in complex analysis being what are called conformal mappings. At least when you avoid places where the derivative is zero, they preserve angles, and that turns out to be useful for many applications. I'm thinking in particular of applications to fluid flow for thin sheets of fluid, idealized two-dimensional fluid. Conformal mappings is useful for that. We're going to see this happen with another example or two as well. You can make vector plots and stream plots of these things, which are examples of things called vector fields. They're pretty, but I'm not going to go into what they are. Oh, I need to enter the function here, the capital Phi function. So it's pretty, but like, what does it mean? That's not so clear. Maybe that's a pretty fluid flow. Probably not realistic. But most interesting to me is thinking about the mapping behavior of these functions. In a sense, trying to graph them at once in terms of how the transformation maps different regions like squares. For example, this is going to show me a square in the plane where x and y both go from 1 to 2 to start off with. And as I animate this mapping, what I'm going to see is I'm going to see how the squaring mapping, f of z equals z squared, transforms it. And what I want you to watch for in thinking about this is the geometric interpretation of multiplication, where the lengths are getting multiplied and the angles are getting added. X and y both go from 1 to 2 here. As I move this slider, we see the effect of the transformation. The lengths are being multiplied and the angles being added. The image of that square is that set right there. Also notice those curves are crossing at right angles too. It's a conformal mapping. The original curves, kind of hard to see, are some vertical and horizontal lines. Yeah, it's too small to see. As I transform it, at any time under the transformation, you see those curves. It's really only the beginning and ending sets that we're truly most interested in representing what goes on with z squared here, but it's kind of fun to think about what's going on in between. That's that square. I could change the square. I could, for example, center it to be at the origin, for example. So here I have a square at the origin, centered at the origin. Watch what happens to this one. It's a little bit more confusing. I'm transforming it. It's kind of folding in on itself, almost like a fish eating something there on the left. It's kind of folding in on itself, and the image gets crossing over itself, reflecting the fact that z squared is not 1 to 1, actually. And the ending image set looks like this, though every point in there except for the origin is the output for 2 distinct inputs. It's the image of 2 inputs. But once again, you got those curves crossing at right angles. Conformal mapping. Except where the derivative is 0 at 0. Does this function have a derivative? Yes, it does. We'll come to that. Here's another example. The inverting map. F of z equals 1 over z. Let's write that down. New example. F of z equals 1 over z. Could be thought of in terms of real and imaginary parts as u plus iv equals w equals f of x plus iy. That's the z. So z is the independent variable and w is the dependent variable, if that was not clear. I'm doing 1 over x plus iy. What do I do with this? Like we saw last week, we can do division by multiplying the top and the bottom by the complex conjugate of the bottom. It's got the same real part, but the opposite imaginary part. When I do that multiplication on the bottom, the i's go away. That's why we do it. But since I don't want to change the output here, I need to also multiply that by this same thing on the top, so that this expression is nothing other than a big 1, as long as I'm not dividing by 0, as long as x and y are not both 0, which you would want to avoid anyway. You don't want to divide by 0. On the top, 1 times x minus iy is just x minus iy. On the bottom, this is a minus sign here. First times first is x squared. Outside times outside is minus ixy. Inside times inside is plus ixy. And those will cancel. That's what we liked. And then last times last is minus I squared y squared. These two cancel. This becomes a plus y squared. And then you can break this fraction into two pieces. One that does not involve I at all, x over x squared plus y squared. And then the other one, factor out the I from the top there, and you're left with minus y over x squared plus y squared. So for this function, for this example, the u function is that, and the v function is this. And once again, we're interested in looking at the graphs of these things, and also maybe thinking of this as a mapping. Transformation of the plane. I could create a new capital phi function. If I like, let's go ahead and do this first. I can do a complex expand that will confirm what I just did. There it is. I can do other things that I haven't done yet. I could also graph the modulus of the output. This expression that I'm highlighting right there is the absolute value of W, the modulus. Distance to the origin of the output. I could graph that as an ordinary multivariable calculus function. What's its formula? It would involve a square root of u squared plus v squared, Pythagorean theorem. I'm just having Mathematica do it with ABS here. Interesting. With this function, I've got some sort of higher dimensional vertical asymptote. Yes, that's what you're seeing there. As z approaches 0, meaning x and y approach 0, the output of this function in absolute value, the distance to the origin, gets large, goes to infinity. Can make a contour plot of that as well. That's kind of wild. It's like a white hole instead of a black hole. By the way, in astronomy, there are white holes. You know, you've heard of black holes. There are actually white holes too, at least theoretically. I don't know if anybody's actually observed one. You can go ahead and enter U and V. You can look at their contour plots side by side. Oh, wow, those are pretty. You could show their contour plots in one pretty picture and see if they are crossing with perpendicular angles, 45 and 90-degree angles. Yes, it looks like they are. Anytime those touch, it's a 90-degree angle, technically, of their tangent lines. We could look at the stream plot. Again, I'm not explaining what this is, so that's not very interesting. Oh, and I need to enter that again. There we go. Okay, it's not super interesting in that case. We could also think about the mapping properties. And here what I'm going to do, this is kind of wild. Well, let's start off with a different square. Let's start off with the same square we started with in the last example. X and Y both go from 1 to 2. And let's zoom in near the origin here a bit. Okay, so here I have the square where X and Y go both between 1 and 2. What is the image of this square under this 1 over z inverting mapping? Watch it here. It's being shrunk and twisted. The image looks like that. You can barely see it, but there's curves in there that cross at 90-degree angles. That's the image of this square. X and y go from 1 to 2. What about an image of a square where x and y go from, say, 0.5 to 1? Now I'm starting closer to the origin. Actually, I think I want to change it a bit. Let's go 0.25, 0.75. Yeah, or 0.5. Kind of small square near the origin. What's going to happen to it? It's going to go away from the origin and get bigger. So the square that started out further from the origin went across and got smaller. This one that's starting close to the origin and is small is once again going across the real axis and getting bigger as we go. Why? It's related to the function being 1 over z, just like 1 over x. Ordinary graph looks like that, and takes small areas near 0 and maps them to large numbers far away from 0, and takes bigger numbers and maps them to small numbers. That's what's going on here with the complex numbers too. It gets even more extreme. If I go from, say, 0.01 to 0.1 in both the x and y directions here, that's a really small square near the origin. But when I map it, so you enter this, you can barely even see it. This little kind of dot down there, that's the square. I map it under 1 over z, what happens to it? It gets a lot bigger. Okay? And the angles are still preserved, 90-degree angles there. Next example. Exponential map. F of z is e to the z. What should it be by hand? U plus iv equals is w, is f of z is f of x plus iy. Don't be bothered by the fact that I'm doing a bunch of different symbols for the same thing here. Is, okay, let's write it as e to the z initially. E to the z. Take e and raise it to an arbitrary complex number power. What in the world does this mean? You can define it with a series. You can define this with the Taylor series centered at 0. Essentially take this as a definition. And that is fine, but it's not very helpful, seemingly, in terms of understanding what's going on. What's a bit more helpful ultimately is, well, you could do the same thing I did with the most beautiful equation in the universe, e to the I pi plus 1 equals 0, and replace these z's with each with x plus iy, do some fancy manipulations and rearranging. It's a little complicated because you're squaring this, you're cubing it, you're raising it to the 4th power. You have to use the binomial theorem, and it's kind of complicated. I'm not going to go through those details. Instead, another way to approach it is to, well, effectively assume this is true. Assume that property of exponents can be used to separate that as a product. You could prove that maybe from this definition, or you could take this as just a definition here. It's all a matter of style. And then you still would use the series for iy, just like we did with e to the I pi plus 1 equals 0, to represent e to the iy as cosine of y plus I sine y. Do you remember? What was it, 2 weeks ago? We proved, well, hand-wavy proof, that e to the I pi plus 1 was 0, the most beautiful equation in the universe, right? If you get abducted by aliens and they ask you, that's the answer. That's the most beautiful equation. They might look at our notation and say, I don't understand. they wouldn't speak English either, but it's the most beautiful equation, and they would know about it. That's what I'm using there to go from here to here without showing the details. Then expand this as e to the x cosine of y plus I e to the x sine of y. And if you do so, what we've got here are formulas for u and v again. There's u, and here's v. The real part and the imaginary part. Exponential functions and trig functions are intimately related to each other, amazingly. You never expect that, right, before this point. When you deal with complex numbers, exponential functions, e to the z in this case, and trig functions, cosine and sine, are intimately related. Amazing. And then you can do the same kinds of things. You can do the complex expand here to confirm what I just did. This needs to be rewritten here. Let me enter this. And let's replace this with u of xy plus plus I sine of x, v of xy. I can graph the modulus of the output. Interesting. Kind of seeing an exponential behavior there, aren't we? I can make a contour plot of that as well. I won't. I can make a contour plot of u and v individually, the real and the imaginary parts. Interesting. Look at those. Once again, the outputs are getting higher where the shading is lighter and lower where it's darker. This is the graph of e to the x cosine of y as a multivariable function. This is the contour map of e to the x sine of y as a multivariable function. Plot them both in the same picture, and they do intersect at right angles. Define your transformation, your mapping, and see mapping properties. Maybe also the stream plot. Is it pretty? Yes, that's kind of pretty. Okay, here's again what I'm most interested in. I'm starting with a small square here. What's its image? Is it going to be a large square or not? I think not much, too much larger, but something is happening to it. Let's go and zoom in closer. So something is happening to the square, but not much. This seems like a boring mapping compared to the others. I think if I move the square, more interesting things can happen. Okay, yeah, it's a bit more interesting. We're looking at images. Again, angles are preserved, conformal mapping. Anyway, you can do this. You can do it for cosine and sine. You can do derivatives of complex functions, like if f of z is z squared, that does mean the derivative is 2z. And if f of z is 1 over z, z to the negative 1, then f prime is negative z to the negative 2, negative 1 over z squared. And if f of z is e to the z, f prime is still e to the z. All those kind of rules still work. What does it mean? Does the derivative give you a slope? No, it's more complicated, but it's still beautiful, and it's still related to the geometry of complex multiplication. Moduli getting multiplied, angles getting added. It's still all related. If you're interested in looking up the geometric interpretation of derivative, I would encourage you to Google the word amplitwist. You might find some stuff I've talked about if you do that search, and more officially, something that's other people have done that's probably more thorough than what I've done. Amplitwist is related to the geometric interpretation of the derivative. And it's, again, really cool. You can relate it to the mapping properties. You can understand the mapping properties that way. Can you integrate complex functions? Of course, why not? You can differentiate, then you can integrate. if you get into the subject, there's something called the residue theorem, which sounds like it must be the most boring theorem in the world. Residue theorem. But it's actually one of the coolest theorems in the world. The residue theorem, I'm not saying it's easy. It would take months to get there, months of study. But if you can get there after your months of study, it's completely unexpected result related to complex integration. And you can use it to do amazing things with real integrals. You can use the residue theorem to evaluate certain real integrals where you couldn't do it any other way. So it gives you a powerful tool to do things you couldn't solve any other way. It's really astonishing, to tell you the truth. It's an amazing theorem.